The story of the James Webb Space Telescope does not begin with its spectacular launch from French Guiana in 2021. It begins with a fundamental crisis in cosmology that was discovered decades earlier. To understand why humanity spent 30 years and $10 billion on a single instrument, we must first understand the limitations of our most beloved icon, the Hubble Space Telescope. For over 30 years, Hubble provided us with a window into the divine. It captured the pillars of creation in the Eagle Nebula, showing us giant stalks of interstellar gas and dust where stars are born. It gave us the Hubble Deep Field, revealing thousands of galaxies in a tiny, seemingly empty patch of sky. But as Hubble tried to look further and further back into the history of the universe, toward the era of the very first stars, it hit a wall. This was not a physical wall, but a wall of physics known as cosmological redshift. Narrative expansion. The physics of the expanding balloon. Imagine the universe as a vast, inflating balloon. If you draw a wave on the surface of that balloon, as the balloon expands, the wave itself is stretched. This is exactly what happens to light. The universe is expanding, and space itself is stretching. As light travels from a galaxy 13.5 billion light-years away toward Earth, the very fabric of the vacuum through which it moves expands. This expansion pulls the light waves, increasing their wavelength. A photon that started its journey as high-energy ultraviolet or blue light billions of years ago has been stretched so severely by the time it reaches our solar system that its wavelength has increased by a factor of 10 or 20. It has been pushed out of the visible spectrum and into the long, cool wavelengths of the infrared. To Hubble's glass mirrors and silicon sensors, the earliest era of the universe, the period we call the cosmic dawn, was pitch black, not because there were no stars, but because their light had been redshifted out of our sight. This created the primary mission for the next generation of telescopes. If we wanted to see the first stars, the so-called population 3 stars that were born from the raw hydrogen and helium of the Big Bang, we had to build a machine that didn't just see light, but sense the faintest whispers of heat. We had to build an infrared sovereign. The necessity for infrared goes beyond the redshift of distant galaxies. It also addresses one of the most frustrating obstacles in astronomy: interstellar dust. The universe is an incredibly dusty place. The regions where stars and planets are born are filled with thick clouds of silicates and carbon-based grains. These clouds are opaque to visible light. They act as a cosmic curtain that absorbs and scatters shorter wavelengths. Technical detail: Mies scattering and Rayleigh scattering. When Hubble looked at the center of our galaxy, it saw a wall of black dust. The visible light simply could not penetrate the dense gas. However, infrared radiation has a longer wavelength, allowing it to pass through these dust grains as if they weren't there. It is a phenomenon similar to how a lighthouse beam can penetrate a thick fog that would block a simple flashlight. By building the James Webb Space Telescope to operate in the near-infrared, NR, and mid-infrared MIR, NASA, ESA, and CSA weren't just looking further back in time. They were looking through the obstacles of the modern universe. They were enabling us to see the protostars hidden deep within the Orion Nebula and the center of the Milky Way. But this capability introduced the greatest engineering paradox in the history of the space program: the thermal noise problem. Everything that has a temperature above absolute zero emits infrared radiation. You emit it. The Earth emits it. Even the telescope itself emits it. If the James Webb Telescope were at room temperature, its own heat would drown out the signals from the distant universe. It would be like trying to take a photograph of a faint firefly while standing in front of a blinding searchlight. To function, the telescope had to be cold, unimaginably cold. It had to be kept at a temperature below 50 Kelvin, minus 370 degrees Fahrenheit. This requirement dictated every single design choice for the next 3 decades. The most iconic feature of the JWST is its 6.5-meter primary mirror, composed of 18 golden hexagons. But what lies beneath that gold is a story of extreme material science. At 6.5 meters, a traditional glass mirror like Hubble's would be far too heavy to launch on any existing rocket. Engineers needed a material that was lighter than aluminum, stronger than steel, and, most importantly, capable of maintaining its shape to within nanometers while experiencing the most extreme temperature swings in the solar system. The material they chose was beryllium. The material science of beryllium. Beryllium is a rare, alkaline earth metal, often described as a miracle metal in aerospace engineering. It has one of the highest melting points of the light metals and an incredible strength-to-weight ratio. But it is a nightmare to work with. It is toxic if inhaled as dust, and it is notoriously brittle at room temperature. The process of creating Webb's mirrors was an odyssey that spanned the United States. The ore was mined in Utah, then sent to Ohio to be processed into high-purity powder. This powder was then pressed into massive rectangular blocks in Alabama. From there, the blocks were machined into hexagonal segments, leaving a ribbed structure on the back to reduce weight while maintaining rigidity. Each segment, despite being 1.32 meters in diameter, weighs only 20 kilograms. The most difficult part was the cryogenic polishing. Since beryllium changes shape slightly as it cools, engineers had to polish the mirrors at room temperature into a distorted shape so that when they reached minus 370 degrees Fahrenheit in space, they would warp into the perfect parabolic curve. This required years of testing in the X-ray and cryogenic facility at Marshall Space Flight Center. The precision required was staggering. The surface of the mirrors had to be smooth to within 20 nanometers. To put this into perspective, if one of Webb's hexagonal mirror segments were the size of the entire United States, the highest mountain or imperfection on its surface would be less than 2 inches tall. Once the beryllium segments were polished to perfection, they looked like dull, silver-gray slabs. To become a world-class infrared telescope, they needed a coating. While silver or aluminum are excellent reflectors of visible light, they are surprisingly poor at reflecting infrared. The answer was gold. Gold is the most efficient reflector of infrared radiation in the natural world, reflecting over 99% of all infrared photons that hit its surface. But you cannot simply paint gold onto a mirror. The mirrors were placed in a vacuum chamber where a small amount of 24-karat gold was heated until it turned into a gas. This gold vapor then drifted onto the beryllium surface, forming a layer only 100 nanometers thick. The scale of the coating. This layer is roughly 700 atoms deep. To understand how thin that is, consider that a human hair is about 1,000 times thicker than the gold coating on the James Webb mirrors. The total amount of gold used for the entire 6.5-meter primary mirror is only about 48 grams, roughly the mass of a golf ball. Yet, it is this incredibly thin, golden veil that allows the telescope to capture light that has been traveling through the void for 13.5 billion years. But the gold and the beryllium were only the beginning. The mirrors were ready, but they were still on Earth. To get them into space, to the cold, dark stability of the L2 point, NASA had to solve a problem that many thought was impossible: the origami challenge. If the golden mirrors are the eye of Webb, the sun shield is its parasol. As we discussed, for the telescope to see the heat of the first stars, it must be kept at temperatures below 50 Kelvin. But Webb lives in a solar system dominated by a massive nuclear furnace. The sun, additionally, it must contend with the infrared glow of the Earth and the Moon. The engineers at Northrop Grumman were tasked with building a barrier that could block the massive thermal energy of the sun while being light enough to launch. The result was a 5-layer sun shield, the size of a tennis court, about 21 meters by 14 meters, made of a specialized material called Captain. The material science of Captain. Captain is a polyimide film that remains stable across an enormous range of temperatures, from nearly absolute zero to over 400 degrees Celsius. However, a single layer of Captain wasn't enough. The sun shield uses 5 distinct layers, each separated by a vacuum gap. This is the same principle as a thermos or double-pane window, but on a gargantuan scale. Each layer is incredibly thin. Layer 1, the side facing the sun, is only 0.05 millimeters thick, about the thickness of a human hair. The other 4 layers are even thinner, at 0.025 millimeters. To enhance their thermal properties, each layer is coated with aluminum, and the 2 sun-facing layers have specialized doped silicon coating to reflect the sun's ultraviolet radiation. The thermal gradient. The engineering magic of these 5 layers is found in the thermal gradient. On the hot side of the sun shield, The first layer is blasted by solar radiation, reaching temperatures of up to 110 degrees Celsius, 230 degrees Fahrenheit. However, because each successive layer is slightly larger than the one below it and separated by a gap, the heat is redirected out of the sides and back into space. By the time you reach the fifth layer, the temperature has dropped to a staggering minus 235 degrees Celsius, minus 390 degrees Fahrenheit. This 300-degree temperature difference occurs across a distance of less than a few feet. It is the most efficient thermal insulator ever flown in space. Because the sun shield and the 6.5-meter mirror were too large to fit into the 5-meter-wide fairing of the Ariane 5 rocket, the entire telescope had to be folded. This introduced a level of mechanical complexity that had never been attempted in the history of exploration. In aerospace engineering, a single point of failure, SPOF, is a component, a motor, a release pin, a cable that has no backup. If it fails, the entire mission is over. Most satellites are designed to have as few SPOFs as possible, usually fewer than 20. The James Webb Space Telescope had 344. The mechanical ballet. Once Webb reached space, it began a 14-day sequence of deployments often called the Weeks of Terror. The momentum flap, to balance the pressure of the solar wind hitting the massive sun shield. A small flap had to deploy to act as a rudder. The deployable tower assembly. The telescope mirrors had to be physically lifted away from the warm spacecraft bus to allow for cooling. The sun shield unfurling. This was the most dangerous part. The 5 layers of Captain were folded like a parachute and held in place by 107 membrane release devices, pins. If a single pin failed to fire, the shield could snag and tear. Tensioning. Once unfurled, the layers had to be pulled taut by a series of pulleys and high-strength cables. There were 90 of these cables, weaving through the structure like tendons in a human hand. Every one of these movements was powered by a motor. There were 178 release actuators and dozens of hinges. Because these motors were in the vacuum of space, traditional lubricants like oil would evaporate or freeze. Engineers had to use dry lubricants and specialized heaters to ensure that every gear turned exactly when it was supposed to. There was no reset button. There was no way to send an astronaut to fix it. Hubble was in low Earth orbit and could be serviced by the space shuttle. Webb was headed for the L2 point, 1.5 million kilometers away, far beyond the reach of any human rescue mission. While the sun shield keeps the telescope cold enough for the near-infrared, NIR, instruments, it isn't cold enough for the mid-infrared instrument, MIRI. MIRI is designed to see the longest wavelengths of infrared, which are emitted by the coolest objects in the universe. To function, MIRI must be cooled down to just 7 Kelvin, 7 degrees above absolute zero. Passive cooling from the sun shield can only get the telescope down to about 40 Kelvin. To bridge that final gap, NASA developed a cryocooler, essentially the world's most sophisticated refrigerator. The physics of the pulse tube. The MIRI cryocooler uses a specialized pulse tube technology. It circulates helium gas through a closed-loop system. By using a series of pistons and valves to compress and then rapidly expand the helium, the system absorbs heat from a MIRI instrument and dumps it out on the warm side of the spacecraft. This system had to be vibration-free. If the refrigerator vibrated even slightly, it would blur the images of distant galaxies. To solve this, the engineers used opposing pistons that cancel each other's momentum, similar to the Boxer engine design in high-performance cars. The cryocooler is a masterpiece of quantum-level engineering, allowing Webb to see objects so cold they emit no visible light whatsoever. On Christmas Day, 2021, the world watched as an Ariane 5 rocket roared off the pad in Kourou, French Guiana. This was not a routine launch. The rocket had been modified with special vent valves to ensure that the air pressure inside the fairing didn't damage the delicate Captain sun shield as it exited the atmosphere. The fuel paradox. The Ariane 5 performed so perfectly that it placed Webb on a trajectory more accurate than anyone had dared to hope. In space travel, every gram of fuel is precious. Webb carries a limited supply of fuel to maintain its orbit at L2. If the launch had been slightly off, Webb would have had to use its own fuel to correct the course, shortening its mission life to maybe 10 years. Because the launch was so precise, Webb was able to conserve nearly all its fuel. NASA subsequently announced that the telescope likely has enough fuel to operate for over 20 years. The perfection of the Ariane 5 added a decade of science to the mission's legacy before it even reached its destination. After its perfect launch, the James Webb Space Telescope did not simply travel to a planet or a moon. It traveled to a mathematical coordinate in the void, the second Lagrange point, or L2. To understand why Webb is located 1.5 million kilometers away from Earth, 4 times further than the moon, we must understand the physics of orbital mechanics and the balance of forces. In any two-body system, such as the Sun and the Earth, there are 5 points where a third, smaller object can stay in a fixed position relative to the larger bodies. These are the Lagrange points. The L2 advantage. If Webb were in orbit around the Earth, like Hubble, it would pass in and out of the Earth's shadow every 90 minutes. The massive fluctuations in temperature would cause the beryllium mirrors to expand and contract, ruining the focus. Furthermore, the Earth itself is a giant source of infrared heat. By parking at L2, Webb can keep the Sun, the Earth, and the Moon all on the same side of its sun shield at all times. This allows the telescope to look out into the dark, cold depths of the universe with total thermal stability. The halo orbit. However, L2 is not a solid spot. It is an unstable equilibrium point, like balancing a marble on top of a needle. If Webb sat exactly at L2, the Earth would block the Sun, and Webb's solar panels would receive no power. Instead, Webb performs a halo orbit. It perpetually loops around the empty L2 point in a circle larger than the Moon's orbit. This ensures it always has a line of sight to the Sun for power and to the Earth for communication via the Deep Space Network. When Webb reached its destination, it was blind. The 18 hexagonal segments were folded and misaligned. To the telescope's sensors, a single star looked like 18 separate, blurry dots. The process of turning these 18 segments into a single, cohesive 6.5-meter mirror is known as wavefront sensing and control. The actuators. Behind each hexagonal segment are 7 tiny motors called actuators. 6 of these move the segment in 6 degrees of freedom, tilting and shifting, while the 7th actuator can actually change the curvature of the mirror segment itself by pushing or pulling on its center. The phasing process. Over the course of 3 months, engineers at the Space Telescope Science Institute, SDSCI, move the segments in increments as small as 10 nanometers, about 1/10,000th the width of a human hair. They used a mathematical algorithm called phase retrieval to analyze the blurry images and calculate exactly how much each mirror needed to move. The final goal was to align the mirrors so perfectly that the wavefront error was less than 150 nanometers. When they finally achieved fine phasing, the 18 images of a test star, HD 84406, collapsed into a single, piercing point of light. The telescope was finally focused. It was the sharpest infrared I ever constructed by human hands. In May 2022, before the first official images were even released, disaster struck. A micrometeoroid, a tiny fragment of space dust, slammed into one of Webb's primary mirror segments, C3. While NASA had anticipated impact from small dust particles, this specific hit was larger than any of the pre-launch models had predicted. It left a physical dent in the golden beryllium mirror. For a moment, there was panic. Would this $10 billion machine be degraded before its mission even began? The technical solution. Because Webb's mirrors are active, the engineers had a unique way to compensate. They couldn't physically repair the hole, but they could use the actuators to slightly retilt the other 17 segments and the damaged C3 segment to cancel out the distortion. By applying a mathematical offset to the mirror's shape, they were able to minimize the impact on the image quality. The telescope still exceeds all its original scientific requirements, but the event served as a chilling reminder. Webb is a fragile glass and gold jewel sitting in a shooting gallery of cosmic debris. To mitigate future risks, NASA now restricts the directions Webb can point, ensuring it rarely flies into the wind of incoming micrometeoroid streams. In the summer of 2024, Webb looked deep into a patch of sky and found something that sent shockwaves through the physics community. It discovered a galaxy named JWST Z14-0. This galaxy is seen as it was only 290 million years after the Big Bang. In the grand timeline of the universe, 13.8 billion years, this is the blink of an eye. According to the Standard Model of Cosmology, stars and galaxies take a long time to form. Gravity must slowly pull gas together, stars must ignite, and galaxies must gradually merge. The crisis in physics, JWST Z14-0, is not a small, faint smudge. It is large, bright, and filled with heavy elements like oxygen and carbon. For these elements to exist, an entire previous generation of stars must have already lived, died, and exploded. This discovery presents a massive problem for our understanding of the early universe. How did a galaxy get so big, so fast? Some physicists are now suggesting that dark matter might behave differently than we thought, or that the cosmological constant, dark energy, might have been stronger in the past. Webb is no longer just a telescope. It is a troublemaker that is forcing us to rewrite the first chapters of the book of Genesis. While Webb's images capture the public's imagination, its most profound work is done through spectroscopy. This is the science of breaking light into its constituent colors to reveal the chemical fingerprints of distant worlds. In late 2023, Webb turned its massive golden eye toward a sub-Neptune exoplanet called K2-18b, located 120 light-years away. The physics of transmission spectroscopy: when K2-18b passes in front of its host star, a tiny fraction of the starlight filters through the planet's atmosphere. The gases in that atmosphere, methane, carbon dioxide, nitrogen, absorb specific wavelengths of light. By measuring the dips in the light spectrum, Webb can identify exactly which molecules are present. Technical breakdown: the DMS controversy. The discovery that shook the world was the potential detection of dimethyl sulfide, DMS. On Earth, DMS is a molecule that is produced exclusively by life, specifically by phytoplankton in marine environments. Webb's NIR spec, near-infrared spectrograph, identified a weak signal at the exact frequency where DMS should exist. If confirmed, this would be the first biosignature ever detected on an exoplanet. However, the data is at the edge of the telescope's sensitivity. We are currently analyzing this signal-to-noise ratio to determine if this is a true biological signal or a statistical fluke. Webb is effectively performing a chemical autopsy of a world we can never visit, looking for the breath of alien life in the dark. One of Hubble's most famous images was the Pillars of Creation in the Eagle Nebula. In visible light, these pillars look like solid, majestic towers of cold stone. But Webb's view changed everything we thought we knew about this iconic structure. The transparency of the void. Webb's NIR cam peers through the thick columns of interstellar dust, revealing that they are not solid at all, but semi-transparent clouds of gas. Where Hubble saw dark voids, Webb saw thousands of shimmering stars. Scientific detail: protostellar outflows. The most striking discovery was the lava-like, red spots at the tips of the pillars. These are protostellar outflows. When a star is being born, it collapses under gravity, spinning faster and faster. This process ejects massive jets of material into the surrounding nebula. These jets collide with the gas clouds, creating bow shocks that glow intensely in the mid-infrared. Webb has allowed us to witness the labor pains of star birth with a clarity that was physically impossible for any previous telescope. While NIR cam sees the warm universe, MIRI, the mid-infrared instrument, sees the truly cold components of the cosmos. MIRI is the instrument that requires the 7 Kelvin cryocooler we discussed earlier. Seeing the building blocks of planets, MIRI is designed to look at protoplanetary disks, the swirling rings of dust and ice that eventually form planets around new stars. By looking in the mid-infrared, MIRI can detect the presence of water vapor, silicates, and complex organic molecules like polycyclic aromatic hydrocarbons, PAHs. In the Orion Nebula, MIRI discovered a protoplanetary disk that is being blasted by radiation from nearby massive stars. This data is teaching us how solar systems like our own survive their violent childhood. We are seeing the water that will one day fill alien oceans being formed in the cold silence of interstellar space. The ultimate goal of JWST is to find the population 3 stars. These are the first generation of stars that formed from the pure hydrogen and helium of the Big Bang. They were massive, hundreds of times the size of our Sun, and they burned hot and fast, living for only a few million years before exploding as parent stability supernovae. The chemical enrichment of the universe. Before these stars existed, there was no oxygen, no carbon, and no iron in the universe. Population 3 stars were the cosmic furnaces that forged the elements of the periodic table. When they exploded, they seeded the universe with the heavy elements that eventually formed the Earth and our own bodies. Webb is currently searching for the faint gravitational lensing signatures of these first stars, hoping to capture the exact moment when the Dark Ages ended and the universe was bathed in light for the first time. Chapter 17. Technosignatures. Is anyone building? Beyond searching for biosignatures, like methane or oxygen, Webb is also capable of searching for technosignatures, signs of advanced alien technology. The Dyson Sphere Search. If an advanced civilization built a Dyson sphere around their star to capture its energy, the sphere would emit a specific waste heat signature in the mid-infrared. Webb's MIRI instrument is uniquely qualified to detect this heat. While we haven't found a Dyson sphere yet, Webb is currently surveying nearby M-dwarf stars for any anomalies in their infrared output. We are no longer just looking for life, we are looking for intelligence. The James Webb Space Telescope is more than a $10 billion engineering marvel. It is a testament to the human spirit's refusal to accept the darkness. We build a machine that could fold itself into a rocket, travel 1,000,000 miles into the void, and survive the freezing cold to look back at our own origins. As we look at the images of Jade's GS Z14-0, or the pillars of creation, we're not just looking at distant objects. We are looking at ourselves. We are looking at the atoms that would one day become our DNA, being forged in the heart of ancient stars. Webb has shown us that the universe is far more complex, far more beautiful, and far more impossible than we ever dared to imagine. The Origami time machine has only just begun its journey, and as long as its golden eye remains open, the secrets of the beginning of time will continue to unfold. In most satellite missions, engineers follow a redundancy principle. If a thruster fails, there is a second thruster. If a computer crashes, a backup reboots. But the James Webb Space Telescope was a victim of its own ambition. Its size and weight were so close to the absolute limit of the Ariane 5 rocket that NASA had to make a heartbreaking choice. They had to sacrifice backup systems for scientific capability. Every kilogram used for a backup motor was a kilogram taken away from the golden mirrors or the life-saving fuel. This resulted in 344 individual mechanisms that had to work perfectly. There was no plan B. These were not just nuts and bolts. They were the 344 keys to the survival of human curiosity. The first 30 minutes after launch were the most critical for power. Webb was running on internal batteries that had only a few hours of life. The very first single point of failure was the solar array deployment actuator. If the spring-loaded mechanism failed to unfurl the solar panels, Webb would have died in total darkness before even leaving Earth's shadow. Engineers watched the telemetry data from the Malindi ground station in Kenya, waiting for a single bit of data to flip from 0 to 1. When the panels deployed 33 minutes after launch, the mission survived its first brush with death, but 343 ghosts remained. On the second day, Webb had to point its ears toward Earth. This involved the deployment of the gimbaled antenna assembly. This high-gain antenna is the only way Webb can send its massive 50 gigabit datasets back to the deep space network. If the twin-axis gimbal, a complex set of gears and lubricants, had seized in the cold of space, Webb would be functional but mute. It would be gathering the secrets of the Big Bang, but it would have no way to tell us what it saw. Engineers had to trust in a specialized dry lubricant made of molybdenum disulfide, because traditional oils would have frozen solid or evaporated into a fog that would have ruined the golden mirrors. The most terrifying sequence began on day 3. The sun shield is held in place by 107 individual membrane release devices, essentially motorized pins. For the sun shield to unfurl, Every single one of these 107 pins had to fire in a perfect, synchronized sequence. Technical deep dive. The snagging nightmare. Imagine trying to unfurl 5 layers of plastic wrap the size of a tennis court in zero gravity, using only remote-controlled strings. If just one of these 107 pins had jammed, the sun shield would have snagged. A snag shield would mean the telescope could never reach its operating temperature of minus 370 degrees Fahrenheit. The engineers at Northrop Grumman spent years simulating snag scenarios. They worried about the captain's sheets, which are thinner than a human hair, getting caught on a stray bolt or a piece of thermal tape. During ground testing in 2018, the sun shield actually tore, delaying the mission by years. In the silence of space, there was no one to reach out and unstick a caught corner. Every motor had to pull with the exact Newton meters of force required. No more, no less. Once the sun shield was out, it had to be tensioned. This involved 90 separate cables running through a complex web of pulleys. These cables are the tendons of the telescope. If a cable had snapped under the tension, the layers of the sun shield would have touched each other. This is known as thermal short-circuiting. If the layers touch, heat from the sun-facing side can conduct directly to the cold side, instantly blinding the infrared sensors. The precision required for the tensioning motors was equivalent to pulling a thread through a needle from a mile away. On day 10, the most critical structural deployment occurred: the secondary mirror. This mirror is held by 3 long struts, the tripod. It is the piece that reflects light from the large golden mirror into the instruments. If the latches on this tripod had failed to click into place with sub-millimeter precision, the light from the 13 billion year journey would have hit the primary mirror and then simply bounced off into the void. Webb would have been a giant golden bucket that couldn't pour its contents into glass. The locking mechanism relied on a thermal fit design, using the extreme cold of space to shrink the metal parts into a permanent, immovable lock. When the first deep field images from Webb arrived, cosmologists expected to see small, chaotic clusters of young stars. Instead, they found point sources, objects that emitted as much light as an entire galaxy, but occupied a space no larger than our own solar system. This is the birth of the dark star hypothesis. In the early universe, the density of dark matter was significantly higher than it is today. These theoretical dark stars are not powered by nuclear fusion like our sun. Instead, they are massive clouds of hydrogen and helium, millions of times more massive than the sun, powered by dark matter annihilation. As WIMPs, weakly interacting massive particles, collide at the heart of these clouds, they release pure energy, preventing the star from collapsing into a black hole. These stars would be cool, but gargantuan, with diameters stretching across billions of miles. They are the missing link between the Big Bang and the first galaxies. If Webb confirms their existence, we are no longer just looking at the first light. We are looking at the first shadows, a form of matter that has been invisible to us since the beginning of time, manifesting as the brightest objects in the cosmos. Webb is currently performing what can only be described as cosmic archaeology of the soul. By looking at the chameleon eye molecular cloud, Webb has detected ices containing complex molecules, methanol, formic acid, and even ethanol. The profound realization here is one of chemical continuity. These molecules were formed in the absolute zero of interstellar space, long before the sun or the Earth existed. They exist on tiny grains of dust, shielded by the darkness of the nebula. As a star forms and its planetary disk stabilizes, these ices are delivered to the surfaces of new planets via comets and asteroids. This means that the building blocks of life are not unique to Earth. They are a universal commodity. Webb has shown us that the ingredients for a DNA molecule are floating in the void, waiting for a garden to land in. We are not a chemical fluke. We are a predictable outcome of a universe that has been preloading the ingredients for life for billions of years. There is a war happening in the field of cosmology, and the James Webb Space Telescope has just fired the decisive shot. This is the Hubble tension. For decades, we have used 2 methods to measure how fast the universe is expanding: $H_0. The first method, looking at the cosmic microwave background, the Big Bang's echo, gives us one number. The second method, using Hubble to measure standard candles like Cepheid variables, gives us a different, higher number. Astronomers hoped that Hubble's sensors were simply not precise enough, that the discrepancy was a human error. But Webb has now remeasured those same stars with 10 times the precision. The result? Hubble was right. The gap remains. This is not just a rounding error. It is a catastrophe for the Standard Model. If both measurements are correct, it means there is a fundamental piece of physics missing from our equations. Perhaps dark energy is changing over time. Perhaps there is a new early dark energy we haven't accounted for. Webb has effectively broken the universe. It has proven that the more we see, the less we truly understand about the fabric of reality itself. For decades, cosmologists have proposed that the universe is not a random soup of galaxies, but a structured web. Dark matter, the invisible glue of the cosmos, forms vast filaments that stretch across billions of light years. Galaxies are merely the dewdrops on this invisible spider web. Before Webb, this was largely a mathematical model. Now, it is a visual reality. Technical expansion, the filamentary structure of the early universe. Webb's deep field observations have identified a strand of 10 galaxies that existed just 830 million years after the Big Bang. This 3-million light-year long filament is the first time we have seen the cosmic web in its infancy. This structure is essential because it dictates how matter flows. Narrative depth, the flow of gas. Think of these filaments as cosmic highways. Cold hydrogen gas flows along these dark matter strands, feeding the growth of massive galaxies at the intersections. By observing these filaments, Webb is solving the mystery of large-scale structure. It is showing us that the universe had a skeleton long before it had light. We are seeing the framework of reality itself, a structure so vast that our entire Milky Way is but a microscopic speck on one of its smallest threads. This discovery challenges our simulations. The web appears to be more organized and developed than our cold dark matter models predicted. Webb is a 6.5-meter telescope, but sometimes even that is not enough. To see the very first stars, Webb uses a trick of Einstein's general relativity, gravitational lensing. When a massive cluster of galaxies sits between Webb and a distant object, its gravity warps the fabric of space-time, acting like a giant magnifying glass. The physics of the Einstein ring, this is not a perfect lens. It distorts, stretches, and magnifies the distant light into arcs and Einstein rings. Webb has used this phenomenon to see Earendel, a single star that lived within the first billion years of the universe. Scientific mystery, the magnification limit. Earendel is being magnified by a factor of thousands. Without this natural cosmic lens, even Webb will be blind to it. But here is the mystery. Webb's data shows that Earendel is part of a small, incredibly dense star cluster. This forces us to reevaluate the initial mass function, the rulebook for how many big stars versus small stars are born. It seems the early universe was a factory for blue giants, stars that lived fast and died young, seeding the universe with the iron in our blood much faster than previously calculated. One of the greatest chicken or the egg problems in astronomy is the relationship between supermassive black holes and their host galaxies. We used to think that galaxies formed first, and then a black hole grew in the center over billions of years. The JWST disruption, the baby quasars. Webb has found massive black holes, millions of times the mass of the Sun, existing in the very first galaxies. These black holes are too big for their age. If a black hole grew at the standard Eddington limit, the maximum speed a black hole can eat, it would take far longer than the age of the universe at that point to reach such a size. The direct collapse hypothesis. This is leading to a radical new theory, direct collapse black holes. Perhaps in the early universe, massive clouds of gas didn't break into stars at all. Instead, they collapsed directly into seed black holes. This implies that black holes didn't grow inside galaxies. They might have built the galaxies around them. Webb is showing us a top-down universe where gravity's most extreme objects were the architects of everything we see. To reach our 80,000-word depth, we must also talk about the limitations and the silent zones. There are places in the universe where even infrared light cannot escape. These are the completely obscured nuclei, cons. Technical analysis, the opacity of the nucleus. In some merging galaxies, the dust is so thick that even Webb's mid-infrared light is blocked. In these regions, the density of gas is so high that the physics of radiation pressure becomes the dominant force. The light from millions of stars is trapped in a tiny region, creating a pressure cooker effect that eventually blows the galaxy apart from the inside out. Webb is measuring the outflow velocity of these gas clouds, showing us that galaxies have a self-regulating mechanism. They breathe gas in to make stars, and then exhale gas to stop themselves from growing too large. To understand our own sun, Webb has looked deep into the Orion Nebula, specifically the Trapezium cluster. This is a stellar nursery, a chaotic region where massive stars are being born. But these massive stars are also monsters. They emit intense ultraviolet, UV, radiation that creates a photoevaporation effect. Technical detail: proplyds and the survival of planets. Webb has captured images of proplyds, protoplanetary disks that are being literally stripped away by the radiation of nearby giant stars. Imagine a young solar system trying to form its planets while being blasted by a cosmic blowtorch. Through an IR spec data, Webb is measuring the mass loss rate of these disks. This is critical for our 90-minute narrative because it answers a fundamental question. Is our solar system a miracle? Most star-forming regions are violent. For Earth to form, our sun must have been born in a relatively quiet neighborhood, where our disk was exceptionally resilient. Webb is showing us that planet formation is a race against time, a struggle between the gravity trying to build a world and the radiation trying to dissolve it into gas. Before there were planets, there was ice. Not the ice in your freezer, but interstellar ice, coating tiny grains of dust in the coldest, densest parts of molecular clouds. In 2023, Webb looked at the chameleon-eye dark molecular cloud and performed a deep spectroscopic analysis. The chemistry of the minus 263 degrees Celsius laboratory, in temperatures approaching absolute zero, traditional chemistry should stop. But Webb found something else. It found complex organic molecules, COMS carbonyl sulfide, ammonia, methane, and more complex structures like methanol. The narrative of continuity. This is the prebiotic soup. These molecules form through surface chemistry on dust grains, powered by rare cosmic rays. When Webb detects these ices, it is proving that the ingredients for life are older than the stars. We are not a chemical fluke that happened on Earth. We are the result of an ancient chemical process that began in the dark, cold voids between galaxies billions of years ago. The water you drink today was once a layer of ice on a dust grain, observed by a telescope $1.5 million kilometers away. To add the necessary human weight and historical density to this 90-minute epic, we must address the 30-year war of the JWST. It was nearly canceled multiple times. In 2011, the U.S. House of Representatives moved to terminate the project due to cost overruns. Narrative expansion. The ghost of the Hubble flaw. The shadow of the Hubble flaw, the spherical aberration in Hubble's mirror, haunted the Webb team. If Webb had a similar flaw, there was no way to fix it. This led to the creation of the Integrated Science Instrument Module, ASGIM, testing, the most rigorous vacuum testing in history. The successors, Nancy Grace Roman and beyond. If Webb had failed, the plan B was a decades-long dark age for astronomy. But because it succeeded, it has paved the way for the Nancy Grace Roman Space Telescope, launching in 2027, and the Habitable Worlds Observatory, HWO. While Webb sees the infrared heat, Roman will have a field of view 100 times larger than Hubble, acting as a wide-angle lens to Webb's telephoto lens. Together, they will map the distribution of dark energy across the entire sky, turning the Hubble tension we discussed earlier into a solved equation. In the massive galaxy clusters like SMACS 0723, Webb has detected a faint, eerie glow between the galaxies. This is intracluster light, ICL, the physics of galactic cannibalism. This light comes from orphan stars, stars that have been ripped out of their home galaxies by tidal forces during massive galactic collisions. They wander the empty space between galaxies, belonging to no one. By measuring this ghost light, Webb is calculating the merger history of the universe. It tells us how many galaxies have been destroyed to build the massive clusters we see today. It is a form of cosmic forensic science. Every photon of ICL is a witness to a gravitational crime that happened billions of years ago. For the past 50 years, the $\lambda CDM model, lambda cold dark matter, has been the bedrock of cosmology. It predicts that the universe is dominated by dark energy, $\lambda, and cold dark matter. According to this math, the first galaxies should have been tiny, chaotic, and late. The conflict with reality. But Webb has delivered a cosmic shock. It found galaxies like the universe breakers, SURS 93316 and others, that are simply too massive and too mature for their age. The technical deep dive. If these galaxies are as old and heavy as Webb's sensors suggest, it means one of three things. Dark matter is not cold. It might be warm or fuzzy, allowing matter to clump together much faster than our supercomputer simulations predicted. The speed of gravity. We might need to modify Einstein's general relativity on a galactic scale. Modified Newtonian dynamics. The early dark energy. There might have been an extra push of dark energy in the first few 100 million years that accelerated the birth of structures. Webb is not just finding objects. It is acting as a particle accelerator in the sky. It is testing the most fundamental laws of physics by using the entire universe as its laboratory. We are currently living through a Kuhnian paradigm shift, where the old textbooks are still in print, but everyone knows they are about to be rewritten. While Webb looks back at the beginning of time, it also gives us the data to look into our own future. By observing the movements and gas compositions of local group galaxies like Andromeda, M31, and Triangulum, M33, Webb has refined our collision course calculations. The galactic merger, Milkomeda. In roughly 4 billion years, our Milky Way will collide with the Andromeda Galaxy. Through Webb's infrared eyes, we can see the gas bridges already forming between nearby dwarf galaxies. The narrative of stability. Webb has shown that our galaxy is currently in a state of quenching. We are running out of the cold gas needed to make new stars. However, the collision with Andromeda will be a rejuvenation event. The massive shock waves will compress the gas, triggering a firestorm of new star formation. We are seeing our own destiny played out in the distant Cartwheel Galaxy, captured in stunning detail by Webb, where a smaller galaxy peers through a larger one, creating a ripple of star birth. Webb is our cosmic oracle, showing us that death for a galaxy is merely a transition into a new, more complex form. As we reach the conclusion of this 90-minute journey, we must ask the ultimate question: why does it matter that we built this machine? The participatory universe. The physicist John Wheeler once proposed the idea of the participatory universe. He suggested that the universe exists in a state of quantum uncertainty until an observer looks at it. Before Webb, the first stars were a mathematical probability. By capturing their photons that have traveled for 13.5 billion years just to hit a 100 nanometer layer of gold, we have brought those stars into the realm of human knowledge. We have observed the beginning, and in doing so, we have completed a loop. The James Webb Space Telescope is the ultimate achievement of a biological species that only recently learned to use tools. We are made of the very carbon and oxygen forged in the stars Webb observes. We are, quite literally, the universe looking back at itself. Through Webb's golden eye, the cosmos has gained a memory. As the cryo-cooler hums in the silence of the L2 point, and the golden mirrors catch the faint heat of a long-dead era, we are reminded of our place in the infinite. We are small, yes. Our lives are shorter than the blink of a galactic eye. But for a brief moment in time, we reached out into the void and demanded to know the truth. The Origami time machine will continue to unfold. New galaxies will be found. New chemical signatures of alien life will be decoded. And as long as we keep looking up, the darkness of the dark ages will never truly return. The light is coming, and we are here to see it.